Welcome everyone to our presentation on reinventing pre-filter for efficient video compression. I am Ramzi Khsib, a principal software engineer at AWS Elemental. I am part of the Elemental Video Engine team. The Elemental Video Engine team is responsible for developing and maintaining core video processing technologies. These technologies powers AWS Elemental suite of cloud-based transcoding solutions. Wondering what a video compression engineer actually does? Well, picture this. Endless hours of watching the same video over and over again. Case in point, the crowd run sequence. Since 2008, I've been watching these marathon runners more times than you've actually run. To keep it interesting, I've even started naming each runner. And yes, they're all named after past Emmy Award winners. Why? Because AWS Elemental has won a few technology Emmy Awards. And that's as close I would get to red carpet fame while watching silent marathon in pixelated slow motion video. While we may joke about the endless hours spent analyzing video frames, there is a serious payoff to all this attention to detail. And since we are at the Video at Scale conference, let's dive into a practical example of how this effort translates to significant cost saving in CDN. Imagine you have a 60 minutes video. This video is being watched by 100K viewers. If we have the technology to reduce the bandwidth by 1 gigabits per second, the total CDN cost will be a whopping 45 terabytes of CDN cost. When it comes to improving video compression efficiency, we have several tools at our disposal. We can develop novel coding tools, optimize existing ones, or focus on specific scenarios. Today, we'll be focusing on pre-filtering input videos as a powerful method to enhance compression efficiency. While new generations of codec offer significant improvements, they come with the challenges. They require new decoders, often have higher compute costs, and can be difficult to deploy. This is why we're exploring pre-filtering as an alternative approach. The core idea behind pre-filtering is to reduce video complexity before compression. This can be done through techniques like motion compensated temporal filter or by directly filtering original pixels. By reducing complexity upfront, we can achieve compression downstream. Input video pre-filtering offers several key advantages. It's codec agnostic, meaning it can work with any compression standard. It does not require changes to the decoder, which simplifies deployment. It can provide significant efficiency increases, and is particularly effective for noisy content. These advantages makes input video pre-filters a highly desirable tool for optimizing video compression. Input video pre-filters have been proposed in many encoders starting from VP9 down to the AVM encoder. The majority of these implementations follow the paradigm of pixel-based motion-compensated temporal filtering. While these filters achieve the sought-after reduction, they introduce objectionable artifacts that limits the adoption of such filters in production workflows. As these filters operate on the original pixels, once these artifacts are introduced, the repercussions on quality are significant. While these filters offer a 5 to 10% compression efficiency, there is small adoption in these filters in premium and broadcast live productions for two main reasons. One, these filters destroy the creative intent. And two, these filters, most of the time, they don't run in real time. So this is the agenda for today. So first, we'll take a closer look at pixel domain filters, which are at the heart of these filtering techniques. Then I will introduce alternative filtering, highlighting their strengths and limitations. After that, I'll walk through the proposed design for creating non-destructive production-ready input filter. Finally, we'll wrap up with results and key takeaways. So how to design an input filter ready for production? To answer this question, let's start by reviewing the core of these filters, the pixel domain input prefilters. At the heart of the pixel domain filter is a weighted average between the current block to filter, P, and two candidate block Q. The weighting function can follow the bilateral with the spatial and range filtering, or the non-local means on finding similar patches across the image. HM in its 16.2 proposed a pixel-based temporal filter that uses a weighted average between motion compensated blocks to filter the input frame. HM follows the bilateral weighting average with the QP scaling added by rate control. The VVC temporal filter builds on the HM approach with several improvements. It modifies filter weights based both on absolute and relative block differences and incorporates a frequency metric to apply stronger filtering to higher frequencies content. The AOM AV1 temporal filter takes a different approach. It uses a non-local mean model, operates on a block basis rather than on individual pixels, and incorporates adaptive noise level estimation. The filter weights in AV1 are calculated based on several factors: motion quantity, noise level, quantization level, and overall filter strength. This allows for adaptive filtering that can be adjusted to different types of noise and content. While pixel-based filter can be effective, they can also introduce visual artifacts. Here we see examples of blocking artifacts, excessive blurriness, a loss of texture. These issues are particularly objectionable at higher and mid bitrate. To illustrate that, let's take these few examples. As these filters operate on a block-based approach, discontinuities around block boundaries will be visible. Another example, for high complex motion or highly textured areas, we notice a loss of texture and noticeable blurriness. Another example of introduced artifact, you can see bending artifacts visible on the window. Film grain is obviously a killer content for filter like input pre-filters. And you can see on the right, film grain is completely wiped out. So to summarize, although input pre-filtering can be effective in enhancing compression efficiency in presence of noise, it is generally not recommended for use with mezzanine and pristine content due to its heavy dependence on the quality of motion estimation. Now let's turn our attention to frequency domain filters, which offer a different approach to pre-filtering. At the heart of frequency domain filtering, the idea of DCT filtering. And DCT filtering was one of the first filters in the frequency domain. It transforms the image to DCT domain, applies a threshold to remove noise, and transforms back to pixel domain. This can be an effective way to denoise while preserving important image structures. In addition to pixel domain filtering, transform domain filtering combined with collaborative filtering presents a compelling alternative. State-of-the-art filters like BM3D continue to be highly effective, even in the face of newer deep learning-based filtering technique. Once similar patches are grouped in a 3D stack, This 3D stack is then transformed to transform domain using a transform like the DCT. Thresholding is applied in the frequency domain, and then inverse transform is applied to go back to the pixel domain. While BM3D is a highly effective solution, it requires an extensive manual tuning to find the optimal sets of parameters. Here you can see the 25 parameters you need to tune to find the perfect filtering setting. So both pixel domain filters and temporal domain filters have their strength. Pixel domain filters often achieve great bandwidth reduction, but usually they soften texture, wipe out film grain. Transform domain, on the other hand, tend to preserve more of the texture, but they are computationally intensive and they cannot be used in real time. So it's worth mentioning that deep learning-based filters are also emerging. While they offer powerful filtering technique, they often come with high computational costs and potential latency issues, which can be challenging for live video applications. Now, let me introduce our proposed filter solution, which aims at combining the strengths of different filtering approach. In designing our filter, we followed several key principles. So one, we wanted a dual domain approach suitable for live encoders. It needed to preserve texture like film grain and, of course, reduce bandwidth while being aware of rate control constraints. Pixel domain filters are superior in terms of bandwidth reduction, but they come at the cost of visible artifacts. On the other hand, transform domain filters are great in terms of preserving texture, but they're harder to tune. Aggregating the results of these two filters is non-trivial. So the question is how to solve these two problems. So to address the limitation of existing filtering techniques, we introduce a new perceptual thresholding module. A key component of our system is this perceptual threshold module. This technology computes filtering strength, perceptual thresholds, aggregation weight, ensuring that our filtering is optimized for human perception. So for optimal visual results, instead of the constant thresholding technique we've seen before, filtering thresholds are computed based on the input characteristics and take into account the human visual system. So our approach is informed by models of the human vision system. So we consider factors like contrast sensitivity, texture masking, luma adaptation, motion aliasing, and many more to ensure that our filtering aligns with how humans perceive video. The contrast sensitivity function, or CSF, is a mathematical model that describes how human visual system perceives contrast at different spatial frequencies. What's interesting is CSF divides the plane in two distinct regions, the visible frequency region and the invisible frequency region. And it's clear that we can filter in the invisible frequency region all the non-discernible frequencies. Second model in perceptual thresholding module is texture masking. So to illustrate texture masking, let's take two example blocks. The block on the top is part of a highly random complex crowd. The block on the bottom is a clear uniform edge. So if we add Gaussian noise to both, it is clear that the crowd block hides or masks noise. It's really hard to see noise on the top block. And on the bottom block, visibility of noise is clear. So using this idea, it is clear that filter strength needs to account for the underlying content. And this could be extended also to film grain. Another aspect of HBS is motion aliasing. And the idea is sensitivity drops with high motion. And I challenge you, when you have a fast band like this one, a soccer game, to read the numbers back on the players. For optimal filtering, as the visibility of artifacts changes with quantization, blurriness is actually more tolerable with coarse quantization. So the proposed filter needed to account for this. Combining the in-loop block-based filtering aspect with the HBS model, we define a rate control aware threshold. The final step in our process is aggregation. So in this aggregation step, we combine the results from our spatial and transform domain filter. We use a sigmoid scaling function to determine the optimal weights for this combination. So now let's head to the results. So the first result is in terms of bandwidth reduction. And using VMath, we're able to measure that we achieved between 6 to 15% in BD rate improvement. But we didn't stop there. We wanted to measure from a subjective perspective. So we had a panel of GoldenEye or expert viewers, and the aggregation of the results showed we have a reduction of 6 to 12%. And also it's noteworthy that these filters are ready to run on real-time processing. So as an example, it takes only 18% of an ABC encoder. What is important with this filter is its non-destructive nature. So it aims at reducing the bandwidth while preserving the creative intent. To illustrate the filter effectiveness, here you can see 1 megabits per second reduction achieved without noticeable quality loss. On the left, we have the original. On the right, we have the filtered version. It is extremely difficult to detect any differences between the two. One of the key advantages of our approach is how to easily integrate it into existing workflow. It can be enabled with just few clicks, making it accessible for a wide range of users. And let's go back to the cost savings. So the potential cost savings are substantial. To put it in perspective, a 1 megabits per second bandwidth reduction for a video watched by 100K viewers for 60 minutes would save about 45 terabytes in CDN cost over the lifetime of a video, which is substantial. So to conclude, our input pre-filter offers a powerful solution for improving compression efficiency. It is suitable for premium broadcast grade workflows, delivers on both efficiency and cost savings, and works well for both real-time and on-demand scenarios, all without requiring a new codec. I'll wrap up my talk where I started. Just like the runners in Crowd Run, who've been looping endlessly for years. Many compression engineers hold up Big Buck Bunny as their gold standard. Let's be honest, optimizing for a cartoon bunny is not exactly the pinnacle of a challenge. The real test? Crowd Run. That's where the action and the real compression magic happen. Thank you all for your attention. I hope you found this presentation informative. Please do reach out if you have any questions.